All right, guys. So review for the final review for test number 3. We're not at our final yet. So this is our review for test 3. Now, I'm not going to go through, I'll walk you through the problems. A lot of these, there's a lot of calculation to do, and I'm not going to have you sit and watch every bit of calculation that's going to be done for these problems. So like number 1, the number of words defined on a page in the dictionary is below. And it wants us, so it gives us a list of numbers, and it wants the mean, the median, and the mode. So in order to find the mean, remember that's where you're going to take all of these numbers and you're going to add them together. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you're going to add those 10 numbers together, and then you're going to divide by 10 because there's 10 numbers. So you add them all together, you divide by 10, and you're going to get 55.1 is going to be your average. That's your mean, okay? The median, to find the median, you have to put them in order from smallest to largest. So 34 would go first, and then 42, and then 45, and then 54, and 58, and 60. Oh, guess what? I already forgot one. 38 is going to go right here. See, that's why we spread them out a little bit. And then 68, and 74, and 78 is going to come last, okay? So to find the median, remember that's the one in the middle. So you're going to cancel out as you work towards the middle. And in this case, we've got 2 numbers in the middle. So rather than using one of those numbers, we have to find the average of those numbers. We're looking for what's in between 54 and 58. In this case, that's easy. That's just 56. If it wasn't nice numbers, you would do 54 plus 58, divide by 2, and that would give you your median. Ours are nice numbers, so it's easy to find the middle one. The mode is the number that just shows up the most, and in this case, they all show up once, so we would select that there is no mode, okay? They all show up once, so there's no mode. There's no number that shows up the most often. Number 2, same thing, mean, median, mode. You're going to take all of these decimals, you're going to add them together, and this time you're going to divide by 1, 2, 3, 4, 5, 6. You're going to divide by 12. So you're going to add them all together, divide by 12, and you're going to end up with 0.1, 0.188. Sorry about that, Bell, because it wants us to round to the nearest thousandth. So be careful when you round that one, 0.188. To get the median, you're going to put those in order from smallest to largest, and you're going to end up with 2 different numbers in the middle again. So you're going to have to add those together, divide by 2 to get the median, and that's going to end up being 0.170. So that tells me that we're going to probably end up with 0.16 and 0.18 as the numbers near the middle, and then you've got to find the average of those 2 numbers and get 0.17. And then it wants the mode, the number that shows up the most. Well, there's 2 0.18s, and there are 1, 2, 3 0.16s. So the mode is going to be 0.16. Now, if there had been more than one, like if 0.18 had happened again, then you would say 0.16 and 0.18. But it only showed up twice, so we only have one mode. All right, moving on. For the following distribution, decide whether you expect the mean, median, or mode to give the best representation. So number 3 and 4 are going to just vary completely based on the situation. What we're considering is outliers. So for example, per capita earnings in New York City. So if we're looking for the average of earnings, we probably don't want to use the mean, because the mean is going to consider all the people, all the homeless people that make nothing. It's also going to consider the people that make an extravagant amount of money in New York City. And so because of those outliers, the mean is probably not the best option to choose. We would probably want to use something more like the median. That's going to give us a better example of what's in the middle, okay? The center of the distribution. So I would choose the median, not because it's easier to calculate, but because it's not affected by those extreme outliers, okay? Number 4, if we're doing the same thing, but we're looking at the snowfall in Omaha, then median, I'm not really worried about outliers when I'm looking at snowfall because I want to consider those outliers. That's important, the amount of snowfall. The mode, I don't think I would consider because I don't want to know the most common snowfall. I want to know all of the snowfall. So I would choose the mean because it's going to consider all the days, not just the no snow days and the big snow days. It's going to consider all of them if I'm looking for the daily snowfall in January. All right, moving on. So again, that one's a little bit opinionated. Number 5, consider the distribution for the monthly sales of ponchos over a 1-year period at Niagara Falls. How many peaks would you expect to happen? Well, I would expect that in the summer, a lot more people visit Niagara Falls than the rest of the year. And I wouldn't really expect another peak in visitors. So I would guess that we're going to get a big peak in the summer months. And I just would expect that one peak. I wouldn't expect another one. So I would say there's probably going to be not many, not 3. There is going to be a peak. I would expect there to just be one corresponding peak to the summer months. Make a sketch of the distribution. It's all of these are going to look pretty similar. In fact, right now, because they're all on top of each other, it's really hard to tell. It looks like, well, I can't tell what one looks like what. So what we're looking for is a pretty standard distribution, except for a peak in the middle of the summer. So I wouldn't expect 2 peaks. I would expect this to happen in the middle of the summer. So you can choose which one based on that. And then part C, are we still going? This is all number 1. What shape would you expect? Well, I would expect it to be a normal distribution. Oh my gosh, bells. This is why I usually record after school hours. But we would expect a symmetric distribution. The summer is going to be the peak. That's going to be the high point in the middle. And then it's going to kind of fade off before and it's going to fade off after. And it would just kind of be centered around those summer months. So I would expect a symmetric distribution for that reason. Okay. And then part D, what variation would you expect? It's probably going to be a large variation because a lot of people are going to probably come in the summer. And then from there, it's going to spread out over the rest of the year. So I would expect there to be quite a bit of variation just because all the different numbers sold the rest of the months is going to vary quite a bit from that peak in the summer. Like in December, I don't think very many ponchos are going to be sold as opposed to in July. So we expect a lot of variation. Okay, number 6. This is going to be something similar. Consider the distribution of the ages of people visiting an amusement park. So how many peaks are there going to be? Again, I would expect there to just be one peak. You're going to have a lot of younger people, and then it's going to spread out from there, depending on the type of amusement park, right? If this is a little kid amusement park, you're going to have a whole bunch of little kids, and then it's going to kind of taper off as the kids get older. There's going to be less and less, and then you're going to have the adults that bring their kids. So I would just expect one peak. Make it a sketch. Well, this is kind of what my sketch would look like. I would imagine lots of young people, and then it would kind of taper off to the right as we get older and older and older. Again, you're going to have to choose the one. They're on top of each other, so I can't tell for that one. C, would you expect the distribution to be symmetric? No, I wouldn't. And that's because when you look at the age of the people that are going, you have a whole bunch of young people, right? But then the age of the older people that are there is going to vary, and it's not really going to end because here you have all your young people, right? You have your 5 to, let's say, 20-year-olds. But then you have some 30-year-olds, and then some 40-year-olds, and then some 50s, and then some 60s, and then there might even be some people in the 70s and 80s. There's not really an age limit going up that's going to visit the park, but there definitely is a minimum age limit that's going to matter. You're not going to have negative 2-year-olds. So I would expect it to be skewed to the right. Remember, this is called a skewed to the right because you have a whole bunch of young people, and then it's going to kind of skew. It's going to get less and less as we go to the right. And we call that a right skewed distribution. Okay. Would you expect, what about the variation? Well, it's probably going to be large because you're going to have a whole bunch of people from all different age groups visiting the park. Okay. All right, number 7. The table to the right gives the cost of living index for 6 East Coast counties and 6 Midwest counties, where 100 represents the average cost of living. All right, so we've got 6 on the left, 6 on the right. Now, it wants us to find the mean, median, and the range for both data sets. I'm not going to do that. I'm not going to find, to find the mean, you would add all of these together and divide by 6. To find the mean for this one, you would add them all together, divide by 6. To find the median, you would put them in order and find the value in the middle. Since there's 6 of them, you would put your 123 and then your 104 would come first, then your 123, then your 128, and then a 134, and then a 141, and then a 314. So as you get to the middle, you're going to end up with these two values. That's the 134 and the 128. You're going to have to add those together and find the average of those two values, which is going to be like 131.7. Okay. The range, you take the biggest value, your 314, and you subtract the smallest value, the 104, and that gives you like 209.7. So you would do 314 minus 104.7, and that gives you the 209.7. All right. And then you would do the same thing with the Midwest. I'm just not going to take time in the video to go through the logistics of doing that. You can type those in and find those values. Part B wants the 5-number summary, which remember is the low number, the high number, the median, and then your quartile 1 and your upper quartile. You are welcome to do that by hand. You can put them in order, but we're going to use technology to do that. So remember, on your TI-84, if that's how you're using this, you would go to stats, and you would go to edit, and you would go to list 1, and you would list all of those stats, the 104, the 128, the 314. You would put all of those in your list. Then you get to go back to second list, and not list, we go back to stats, and you go over to calculate. And if you do 1 var stats and put in list 1, it's going to give those values to you, okay? This first one on top, in fact, that's your average. You could have found your average that way. So what is that? 157.98, because it wants 2 decimals. So that would be your average. And then it wants the 5-number summary, which you can scroll down and find right here at the bottom, okay? So to get my 5-number summary, my low value is right here, my minimum, 104.7. My lower quartile is quartile 1, so that would be 123.6. My median is 131.7. My upper quartile is my quartile 3, which is 141.8. And then my maximum is 314.4. Now, to choose the box plot that matches, remember my box plot is going to be over a number line. So this would be like 100. This would be 200. This would be 300. And let's say this is 400. So my median, my middle number is 131. So up here above 131 would be my middle. My quartile 1 isn't much bigger. That's 141. My quartile 3, my quartile 1, my lower quartile is the 123. And then my low value is just 104, and that would be my lower whisker. Oh my gosh. My high value is clear up at 314. So that would be my big whisker. So it would look something like that. Okay, you've got your low value, your high value, your median with your two boxes that give you your low and upper quartile. Now, as far as section, let's see, the last part of the question wants to know to find the standard deviation for both sets. You go back to your 1-bar stats, and your standard deviation is right here. That SX, that's your standard deviation. So I would say 77.65 is my standard deviation. You can find it for the other data set. Apply the range rule of thumb to estimate the standard deviation. So the range rule of thumb is where you take your range, which, what was my range? I wrote it down before, right? My range is 209.7. So my range rule of thumb, I take my 209.7 and I divide that by 4. So when I do that, 209.7 divided by 4, that gives me approximately 52.43 as my standard deviation. But we found that our standard deviation was actually 78.65. That rule does not work in this case because of that outlier. This one right here, this 314, is a huge outlier, which is going to make my range rule of thumb not work very good. I can't just divide by 4 because of that great big outlier. And I'm guessing the Midwest counties are going to find something similar. Okay. Part 4, based on all the results, compare and discuss the two data sets in terms of their center and variation. Choose the answers that are correct below. So the average COLI for the 6 East counties is higher than the 6 Midwest. I believe it is, which means the average level of COLI for the East is lower. Well, if the average is higher, then that means that the averages are higher. So the mean of the 6 East is higher, so that means that the East counties are higher. So I would choose B. C, the variation of COLI for the East Coast is higher than the West, which means the level of COLI in most Midwest counties varies in a larger range. Or the variation for the East is higher, which means that the variation is lower in the Midwest. So yes, my variation in the East is higher. So that means that the West varies smaller in a smaller range. Well, duh, that's what it's saying. So, all right, number 8, moving on. After recording the pizza delivery times for 2 different pizza shops, you conclude that one pizza shop has a mean delivery time of 46 minutes with a standard deviation of 5 minutes. The other has a mean delivery time of 41 minutes, so its average is lower, but it has a standard deviation of 22 minutes. If you liked pizza from both shops equally well, which one would you order and why? Well, the first shop, I mean, their averages are pretty similar. One is 46 minutes, one is 41 minutes. Those are pretty similar. But the standard deviation of the first shop is 5 minutes. That means on average, the other times are only 5 minutes away from the average time. Whereas this shop, the standard deviation is 22. So that means on average, the other times are 22 minutes away from the average time. That's huge. So even though the averages are nearly equal, that variation is a lot bigger in the second shop. So I would say that A makes sense. And if you like pizza from both shops the same, I would choose the first shop because it's going to have a less variation. It's more reliable. So choose the first shop. The time is more reliable and it has a lower standard deviation. Absolutely. Okay, number 9. 2 airlines have data on arrival times. An arrival time of +7 means the flight arrives 7 minutes early. An arrival time of -4 means the flights arrive 4 minutes late. So this Sky High airline has an average arrival time of 0.5 with a standard deviation of 10.9 minutes. Okay, so that means that they are pretty close to being on time, but they have a large standard deviation. They can be late or they can be early a lot. A lot late or a lot early. Okay, Skyview has a arrival time of -4. So that means it averages -4 minutes late with a standard deviation of 5 minutes. Okay. So explain the meaning of these figures and why they would affect your choice. So the first airline is closer to its arrival time, but on average, when it's late, it's really late. Or when it's early, it's really early. Skyview, it's late a lot more often, but the standard deviation is only 5 minutes. It's a lot more consistent with its times, even though its times are running a little bit late. Okay. So if you want to avoid long delays, or in other words, if you don't want this big long delay, then you would choose Skyview. Skyview Airlines average slightly behind schedule, but they tend to have smaller delays. While Sky High Airlines, they average closer to schedule, but the delays are a lot longer. Okay, so that's the choice. That C would be the best option to choose from, or it's as far as the answers go. Because Sky High Airlines is always better? No, not really. Even though it's on time more often, when it's late, it's really late. Skyview isn't always better because the delays are smaller, but it's also runs late a lot more times. So one is a better situation sometimes than the other. Consider the following set of 3 distributions, all of which are drawn to scale. Identify the 2 distributions that are normal. Which one has a larger variation? Well, normal means that it's centered, right? And it has that centered bell curve. So A and B are definitely normal. This one, C, is right skewed because of this tail sticking off to the right that pulls all of our averages to the right. Now, A and B are the normal distributions, but the larger variation would be A. It has the larger variation because the data is more spread out. They're both normal. This one just has a larger variation because the data is spread out more. This one, the data is clumped a lot closer together in the middle around that average. Okay, 11. State with an explanation whether you would expect the following data sets to be normal. So the weight of 200 new pickup trucks. Well, I would expect that to be normal. They're all getting built by the same, they're all getting manufactured together. If they have a defect, it might cause one truck to be a little bit lighter or a little bit heavier than another. So the data set is expected to be normal since the trucks are all the same make and model. They may be a little way more or less due to a manufacturer defect, making it normal distribution. So that answer right there looks good to me. I could read through the rest. The data set is not expected to be normal. Yeah, I do expect it to be normal. So the only other option would be D. The data set is expected to be normal. Since the trucks are all the same make and model, all of the trucks will weigh the same. No, they won't. They'll weigh close to the same, but they're not all going to weigh exactly the same. Okay, number 12. Assume the resting heart rates for a sample of individuals is normally distributed with a mean of 70 and a standard deviation of 5. Use the 68, 95, 90, 97 rule to find the following quantities. The relative frequency of rates less than 80. Okay, so what it's asking me to do is if it's normally distributed, then it's going to fit on this normal curve, right? And the average, the mean, is 70. So we've got 70 right here in the middle. There's a standard deviation of 5. So that means 75 is right here, and 80 is here. 65 is here, and 60 is here. Because those are each one standard deviation away, right? 75, this is one standard deviation. This is 2 standard deviations, 1, 2 standard. The relative frequency of rates less than 80 using the 68, 95, 90. So less than 80 is all of these people right here. It's everybody less than 80. And when it's talking about using the 68, 95, 99, 99, 7 rule, remember what that means is in between 65 and 75 is going to be 68% of the data. Okay, so we're going to have 34% right here and another 34% right here in between one standard deviation below and one standard deviation above. So 65, that's one standard deviation lower, and 75 is one standard deviation higher, and 68% of the data is going to be in between those two values. 95% of the data is going to be within 2 standard deviations of each direction. That's going to be 98% of, or 95% of the data. Well, we already know that 68% of the data is in this range. So if I take 95 minus that 68, that means that these two sections make up 27%, which means this is going to have 13.5 and this is going to have 13.5% of the data is going to be within 60 to 65. And 13.5 is going to be between 75 and 80. I know I'm going fast because we've already gone through this once. If we need more of an explanation, you can go back to that video's lesson and watch that one. And that also means that 99.7 is within 3 standard deviations, which would be what? 3 standard deviations below would be 55. 3 standard deviations above would be 85. So the way that we can translate this is if 68% of the data is here in the middle and 95% data is here, then from here down, And from here up is going to be that remaining 5%. So you're going to have about 2.5 up here and about 2.5 down here. So when it says the relative frequency of rates less than 80, that's all of this data below 80, except for this little bit that's above. Well, I know that this is 64%, this is 95%, and this little bit right here is 2.5%. So out of the 100% of the data, I'm only missing this group right here, this 2.5. That's what I'm missing. So the percent of data that is going to be under 80 is going to be the 99, or not 99, is going to be 97.5% of the data. So as a decimal, I better write that 0.975, because 97.5 as a decimal is 0.975. So I got that by just adding up all the standard deviations that are there minus this 2.5 that falls outside of my range. Okay. Now the relative frequency of rates greater than 75. So instead of looking at greater than 75 or less than 80, I'm looking at the group that is up here. Okay. Well, I know that this group 75 to 80 is 13.5%, and above 80 is 2.5. So if I take that 13.5 and add the 2.5, that's going to be 16, which is 0.16. And if you wanted to put a 0, you could put 1.60. Same thing. Okay. Now the relative frequency of rates between 60 and 70. So now I'm interested in the group that is in between 60 and 70. So who fits in that group? Well, I know that this is 34% of the data, and this is 13.5% of the data. So when I add those together, I get 47.5%, which is 0.475% of the data. That's my relative frequency. So we've just got to break it up into the sections that we know and add those percentages for each section together. Okay. So 13, use the table to find the standard score and percentile of the following data values. So a data value 1.6 standard deviations below the mean. So if I look at my standard scores, 1.6 standard deviations below the mean is going to be negative 1.6. Remember, my z-score is the standard deviations that I'm below. So I'm 1.6 standard deviations below, which means my percentile is going to be 5.48. And my z-score is negative 1.6 because I'm 1.6 below. Now, a data value 0.8 standard deviations below would be negative 0.8 would be my z-score. And my percentile at negative 0.8 is going to be, where are we? Right here, 21.19. Now you could find that percentile, but it's going to give you the table on the questions that require it. So you don't have to worry about doing the algebra. You just have to use the table. So the standard score for C is 1.2 standard deviations above the mean. So my standard score is going to be 1.2 because I'm above the mean. And that's going to give me a percentile of 88.49 would be my percentile. Okay, number 14. Use the accompanying table of standard scores and their percentiles to find the approximate standard score of the following data values. Then state the approximate number of standard deviations that the value is above or below the mean. So a data value in the 60th percentile. So if I look at this table, if I'm looking at the 60th percentile, that's right around here. Now, 59.87, that's 0.13 away from 60, and 61.79 is 1.79 away. So I'm going to go with the 59.87 because it is the closest to 60 percentile. Okay, it's really close to 60th percentile. And my z-score is 0.25. So I would say that my z-score, the 60th percentile, lies approximately the standard score for the 60th percentile is approximately 0.25. And because it's a positive 0.25, that means that it lies 0.25 standard deviations above the mean. Okay. Now the standard score for the 80th percentile. So 80th percentile is right around here. Now 80.23 is 0.23 above. 78.81 is going to be what? Are we looking at the 80th percentile? Yeah. So that's 1.19 below. This is only 0.23 above. So I'm going to choose this one because it's the closest to 80, and it's 0.85 is going to be my z-score. So I'm approximately 0.85, which is approximately 0.85 standard deviations above the mean. Again, I'm above, and so it's not 0.85. Where are we? Yeah, we're okay. We're at 0.85. And we're in the 80th percentile, so we are above the average. Now, the last one it wants us to find is the 92nd percentile. So I'm looking for what's close to 92. 91.92 and 93.32, but 91.92 is definitely closest. So my z-score is 1.4. So I would say 1.4, which means I am 1.4 standard deviations above the mean. Because again, it's a positive 1.4. Now looking at our number 15, we're not going to do all of them, but I do want to look at this first data value. So we're doing the same thing, but it wants a data value in the 30th percentile. So if I look at that table again, the 30th percentile, I'm right here in between 0.55 and 0.5. Now, this one is 0.85 away from 30, and this one is 0.88 away from 30. So for me, I don't want to use the one that's a little bit farther away. I'm going to use the 0.85. Even though they're really close, this one's a little bit closer. So I would say that the standard score is negative 0.5 because that's my standard score. And what that means is that I am 0.5 standard deviations below the mean. I'm not above the mean now because I'm below. I'm at negative 0.5. So I'm 0.5 standard deviations below the average. The rest are going to be just similar to what you saw before. Okay, 16. Suppose we describe the weather as either hot or chilly. Answer parts A and B. Use the letters H and C to list all possible outcomes for the weather on 2 consecutive days. So you could have a hot consecutive days. You could have a hot and then a cold. You could have a cold and then a hot, or you could have a cold and then a cold. Whoops, that comma shouldn't be there. So you can have hot, 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 cold, cold, hot, or cold, cold. But if we're only interested in the number of hot days, what are the possible events for 2 consecutive days? Well, you could either have 0 hot days, you could have 1 hot day, or you could have 2 hot days. So you could have 0 or 1 or 2 hot days. Number 17, an experiment consists of drawing 1 card from a standard 52 card deck. What's the probability of drawing a red card? So remember, we've got to pick the number of red cards over all of the possible cards. Well, there are 26 red cards out of 52 total cards, which simplifies to 1/2. Please don't put 26 over 2. Always simplify probability. Okay? An experiment consists of drawing 1 card from a standard 52 card deck. What's the probability of drawing a jack? Well, there are 4 jacks out of the 52 cards, which simplifies to 1/13. So that would be your final answer, 1/13. Okay, 19. State whether which method, theoretical, relative frequency, or subjective, should be used to answer the question below. What's the probability of being dealt a 3 of a kind of 4s in a 5-card hand? Well, if I'm looking at the probability of getting a certain hand in a game, relative frequency, I wouldn't want to just keep dealing 5 cards and seeing what comes out to be the best. I also don't really want to use my experience. What are my chances? I want to use theoretical probability. In theory, what's going to be the probability of that happening? And, well, I guess part 2 just wants to know how you would do that, what the method would be. So count all the possible hands with a 3 of a kind of 4s. That sounds pretty good. Drawing 1,000 hands. No, that's relative frequency. Estimating based on experiences. Nope, that's subjective. Drawing hands until a successful hand is drawn. No. Watching a card game tournament. Again, that's subjective. No, I want to count all the possible hands with 3 of a kind where they're 4s. Okay, so number 20. Use the definitions given in the text to find both the odds for and the odds against the following event. So what are the odds of flipping 4 fair coins and getting exactly 1 tails? So here's where we have to do a little bit of counting and probability. If I'm only want to get exactly 1 tails, well, I could get a tails and then a heads, 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 or a heads, tails, heads, heads, or a heads, heads, tails, heads, or heads, 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 and then a tails. So those are 4 different ways that I could get exactly 1 tails. Out of how many possible coin flips? I don't want to list them all, but I can cheat and say, I know that there's 2 possibilities, a heads or a tails on my first flip, and then 2 possibilities, a heads or a tails on my second, and then my third, and then my fourth. So I can do 2 times 2 is 4, times 2 is 8, times 2. There are 16 different possibilities if I flip 4 coins of what I could get. So if 4 of those have 1 tails, that's 4 out of 16. So the odds for getting exactly 1 tails are 4 to 16. Okay. The odds of against, which I would simplify to say 1 to 4, right? Actually, we're doing odds. We're not doing probability. So let's rewrite that. So the odds of getting exactly 1 tails, the probability is 1 to 4. But the odds, we've got to be careful because it says odds. I have one chance of getting tails out of 4, which means I have 3 chances of not getting tails. So the odds against exactly 1 are 3 not getting it to 1 getting it. Remember, when we're doing odds, you don't count. It's a little bit different than probability. Probability is 4 chances of getting it out of 16 total, but it's asking what the odds are. And the odds are the numbers of getting it out of the numbers of not happening. So there's 1 chance of it happening out of 3 chances of it not. Or in other words, this 4 over 16, there's 4 chances of it happening, and there's 12 chances of it not happening. So it's 4 over 12, which is 1 to 3 or 3 to 1. If it said, what's the probability of getting exactly 1 tails, you would say 1/4, but it wants the odds of getting it. So in this one, 2 fair dice are rolled. Find the odds for and the odds against getting a 5 and an even number. Okay, well, my chances of getting a 5, I've got 1 out of 6 chances of getting a 5. And I've got 3 out of 6 chances of getting an even. So that means I have a 4 or a 3 out of 36 chance of getting both, right? Because we're talking about ands. Find the odds for and the odds against getting a 5 and an even number. Well, I guess we better add those together. We don't want to multiply those. Sorry. We want to add those probabilities. My probability of getting a 5 and an even. So if I look at my list of probabilities, so we have a couple of different ways of counting this one. So we're giving ourselves a little bit more space, because what we're looking for is a 5 and an even. So you've got your dice. You want one to be a 5. You want the other one to be an even. So my chances of rolling a 5 are 1 out of 6. And my chances of rolling an even are 3 out of 6. So the chances of getting both of those is 3 out of 36 chances. That's the probability of getting both. But you could also, this one could be an even and this one could be the 5. So there's another way that could happen. This one could be an even, which is 3 out of 6 chances, or this one could be a 5, which is 1 out of 6. So that gives you another 3 out of 36 ways that you could get a 5, right? Because when you add those together, you've got 6 out of 36 ways that it could happen. So that's when I simplify this, there's 6 out of 36 ways that it could happen, which is 1 out of 36 odds. So there's one way that there's 6 out of 36, which is 1 out of 6 ways it could happen, which means there are 5 out of 6 ways that it could not happen, right? If there's 6 out of 36 ways that it could happen, then there's 30 out of 36 ways that it could not happen. So the odds for getting a 5 are 1 to 5. The odds of not getting a 5 and an even are 5 to 1. That is not the same as the probability. The probability of it happening is 1 out of 6 or 6 out of 36. The probability of it not happening is 5 out of 6. But it's not asking for the probability, it's asking for the odds. So remember, the odds are the chances of it happening to the number of ways it could happen to the number of ways that it won't happen. Remember, we would say, if we were to actually write this out all the way, we would say there's 1 out of 6 chances of it happening out of 5 out of 6 chances of it not happening, which gives you that 1 to 5 odds. Remember, odds and probability are different. So be careful on 20 and 21. Okay, 22. Determine whether the following individual events are independent or dependent. Then find the probability of the combined events. So rolling 2 6s followed by 1 3 on 3 tosses of a die. So does it matter what I roll the first 2 times to get me my third roll? No, rolling a dice, those events are independent of each other. So the individual events are independent. The probability of the combined event, so we're going to choose this one B. Now the probability of this event happening, so the way that I find the probability when I'm dealing with independent events, the chance of rolling 2 6s followed by 1 3. So I've got to roll a 6 and then another 6 and then a 3. Well, I have 1 out of 6 chances of getting a 6, 1 out of 6 chances of getting a 6, and 1 out of 6 chances of getting a 3. So I just multiply those all together, which gives me 1 out of 216 chances, right? 6 times 6 times 6, 216. 1 out of 216 chances of this happening, getting a 6, and then a 3. So here's your 1 6, here's your other 6, here's your 3. You just multiply them together. 23, determine whether the following individual events are independent or dependent, then find the probability of the combined event. So the next 10 births at a hospital, all being girls. Well, one child being a girl and the next child being a girl are absolutely independent. They are not dependent on each other. Those individual events are independent. What's the probability of having 10 girls in a row? Well, the chance of having one girl is 1 over 2. And then another girl is also 1 over 2. And then another girl is also 1 over 2. And then another girl is also 1 over 2. And then another girl is also 1 over 2. 1 over 2. Every girl is 1 over 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability of having a girl, I just multiply all those together, which becomes 1 over 2 to the 10th power, which is 1 over 1024. We better double check. 2 to the 10th power is 1024. So that would be the probability of the combined event. You've got 1 out of 1024 chances of getting 10 girls in a row. Probably not very likely, right? But that's the same as the chances of getting a girl, boy, girl, boy, girl, boy, girl, boy, girl, boy, because that's also 1 out of 1024 chances. Okay, 24. Determine whether the following individual events are overlapping or non-overlapping. Then find the probability of the combined event. Now remember, overlapping and non-overlapping is like, what's the probability of getting a queen and a red card? That would be overlapping because some queens are also red. So you can't just count the queens and count the reds. You have to consider the ones that you counted twice. So that's an overlap. Okay, a non-overlap would be like, what are the chances of getting a black card? Or I guess, what are the chances of getting a queen or a 7? Because the queens and the 7s don't overlap. This should be an or right here. Because the queens and the 7s don't overlap, that would be non-overlapping, okay? Because there aren't cards that are queens and 7s. So determine the following. are overlapping, if to get a sum of either 7, 11, or 12 on a roll of 2 dice. Well, if I roll 2 dice, I'm going to add them together and I'm going to get a value. I can't get 2 different values. I can only get 1 value. So these individual events are non-overlapping. Okay. So to get the probability of this happening, you have to take the probability of each one and add them together. Okay. Well, when I roll a dice, I know that there are 36 different possibilities when I roll 2 dice, because one dice has 6, the other dice has 6 possibilities. So that means I've got 36 different combinations that I could get. And how many of those are going to add up to a 7? Now, here's where you've got to... My issue with this question is it's not the question itself. It's that it's asking you to know a lot about dice or to do a whole bunch of math, which we can do. We can do a whole bunch of math. But if you know a little bit about dice and how they work, you know a little bit more information, okay? In other words, as far as the sums of a dice, when you roll dice together, they're either going to add up to a 2 or a 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 or 12. Okay. We've got 36 different possibilities. When you roll a dice, there's 36 different combination of numbers that you can get. There's only one way for those numbers to add up to 2, and that's if you get a 1 and a 1. There's only one way to get a 12. That's if you get a 6 and a 6. But a 3, you could get a 1 and a 2 or a 2 and a 1. And I forgot the 11s. The 11s, you could get a 5 and a 6 or a 6 and a 5. So there's 2 different ways to get a 3 or an 11. Well, let's see. How many different ways to get a 10? You can get a 4 and a 6 or a 6 and a 4, or you can get a 5 and a 5. So there's 3 different ways to get a 10. There's also 3 different ways to get a 2, because you could get a 1 and a 3 and a 1, or a 2 and a 2. 5s, there are how many different ways? 4. Same with 9s, because you could get a 1 and a 4, or a 2 and a 3, or a 3 and a 2, and a 4 and a 1. 6s, there's 5 different ways to get 6s and 8s, and there's 6 different ways to get 7s. Okay. Now, I've played a lot of games with dice, and so I know that these are the probabilities. If you don't know those things, you're going to have to add them all up. Okay. But I know that 7, there's 6 different ways to get a 7 out of 36 rolls. And there's to get an 11, there's 2 different ways out of 36 rolls to get an 11. But there's only one way out of 36 rolls to get a 12. So if I add all of those together, that becomes 9 out of 36, which is 1 out of 4 probability of getting a 7 or an 11 or a 12. You've got 1 out of 4 chances of getting that combination. Okay. 25. And again, I like that question, but it requires you to understand a lot about dice. Or you have to say, okay, well, if I got a 1 and a 1, or a 1 and a 2, or a 1 and a 3, or a 1 and a 4, a 1 and a 5, a 1 and a 6. Well, these are going to add up to 2, to 3, to 4, to 5, to 6, to 7. And you're going to have to consider all those different combinations if you don't play with dice a whole bunch. 25, determine whether the following individual event is overlapping or not, then find the probability. So getting a sum of either 2 or 9. Again, this is non-overlapping, but let's look at how many ways there are to get a 2. Well, there's only one way to get a 2 out of 36. So there's only 1 out of 36 ways of getting a 2. The chances of getting a 9, there are, where's my 9s? 4 different ways of getting a 9. So your probability of getting a 9 is 4 out of 36 chances. So when you add these probabilities together, that's 5 out of 36, the probability of getting one or the other. Okay. 26. Determine whether the following individual events, so same idea, overlapping or not, drawing either a 6 or a face card. Well, 6s and face cards are not the same type of cards, so these are non-overlapping for sure. If this had said a 6 or a red card, those would be overlapping. And what you would have to do is you would have to say, well, there are 4 6s out of 52 cards, and there are 26 out of 52 red cards, but there are 2 cards that are red and they are 4 or 6s. So you would have to add those together, but then you would have to subtract the one that you counted twice. In this case, we don't have to. There are 4 6s, or there are 4 6s out of 52 cards, and there are how many face cards? Well, if you consider kings, queens, jacks, and aces face cards, there are 16 out of 52 face cards, which is 20 out of 52, which simplifies to 4 out of 13 would be your answer. You would have to add the kings, the queens, the jacks, the aces, and the 6s all together. Okay, determine whether they're overlapping or not. I wish there was at least one that was overlapping. But I guess you just saw an example. If it was an overlapping case like that one, you would add those 3, you would add the 2 together, but then you have to subtract the 6s that are also reds. Okay. Determine whether the events are overlapping or not. Randomly meeting a 6-child family with either exactly 1 or exactly 2 children. Well, if you were to meet a 6-child family, the chances that only one of them is a girl of exactly 1 or exactly 2 girl children. Okay, so when you meet a 6-child family, you have a boy or a girl, 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 6 different possibilities. So you've got the total number of possibilities of how many boys and girls you have is 2 times 2 times 2 times 2 times 2 times 2. You've got 2 to the 6 possible families. So that's 64 possibilities, okay? Now, the ways of having exactly 1 girl, the first could be a girl, the second could be a girl, the third could be a girl, the fourth could be a girl, the fifth could be a girl, or the 6th could be a girl. So there's 6 different ways that you could have exactly 1 girl. Now, to have exactly 2 girls, you either have the first 2 are girls, or the first and the third, or the first and the fourth, or the first and the 6th, or the first and the 6th, right? 1, 2, 3, 4, 5, 6. So there's 5 different, if the first one is a girl, right? The first, the second, the third, the fourth, the 5th. But if the first one is a boy, well, the second one could be the girl and have the second and the third, or the second and the fourth, or the second and the 5th, or the second and the 6th. So there's 4 more possibilities. Or you could have the third and the fourth, the third and the fifth, the third and the sixth. So there's 3 more possibilities. Or you could have the fourth and the fifth, or the fourth and the sixth. So there's 2 more possibilities. Or you could just have the fifth and the sixth. So there's 1 more possibility. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You have 15 different ways that you could have 2 girls. So there's only 6 different ways you could have 1 girl. There's 15 different ways you could have 2 girls. So what that adds up to is 21 out of 64 different ways that you could have exactly 1 or exactly 2 girls. We'll find some easier ways to count these, in fact, in the next unit. 28, use the at least once rule to find the probabilities of the following events. Getting at least 1 tails when you toss 8 fair coins. So to get at least 1, that means that the only way to not get at least 1 is if you got all 8 heads. So if I take the probability 1 minus the probability of no tails, remember that formula? The probability of no tails. Well, the probability of no tails only happens if I get all heads. And that's 1 out of, what are my remember my counting principle? If I toss the coin 8 times and I've got 2 possibilities each time, then that's 2 to the 8th possibilities. So 2 to the 8th possibilities. So 1 out of 256 chances of not getting any tails. So that means I have 255 out of 256 chances of getting at least 1 tails. Okay, 29. Explain the meaning of the law of large numbers. Does this law say anything about what will happen in a single observation? The law of large numbers says that as you do more and more and more experiments, your experimental becomes closer to your theoretical, right? As the experiment is done more and more times, that proportion becomes closer to the actual. So we would choose, which one says that? Is that D? As the experiment is done more and more times, the proportion of times that a certain outcome occurs should get closer to the theoretical. So your proportion becomes closer to your theoretical, right? Does this law say anything about what will happen in a single observation or an experiment? No, it does not. Why or why not? Well, this law does not, because what will happen in a single observation, you need to conduct the experiment over 1,000 times in order to find the real probability. And that's not true. The law does not say anything about what will happen in a single observation. Large numbers of events may show some pattern, but the individual events are unpredictable. That's a great answer for B. Okay, moving on. 30. What is an expected value and how is it computed? Should we always expect to get the expected value? Why or why not? Well, our expected value is the estimated gain or loss of when you make a bet, okay? Or the chances of when you buy something of being able to sell it. So the expected value is the estimated gain or loss if you participate in an event, okay? Now, how is the expected value of 2 events computed? Remember, you take the event 1 value times the event 1's probability, and you add all of those events together with their probability. So if there's only 2 events, then you take the probability of event 1 times by the event 1 happening, plus the probability of event 2 multiplied by the value of event 2. So we're going to choose A right there. Then it goes on to say, what should we always expect to get the expected value? Should we always expect to get the expected value? Why or why not? Well, of course not. We should not expect the expected value because the expected value only applies to the two events occurring at the same time. No. We should not always expect the expected value because expected value is calculated with the assumption that the law of large numbers should come into play. Now, this is not always going to happen, but if we do this enough over and over and over and over again, then you can expect that outcome, but not just for doing it once. Okay, 31. You are given 2-to-1 odds against tossing 3 heads with 3 coins, meaning that you win $2 if you succeed and you lose $1 if you fail. Find the expected value of the game. Okay, so we're looking at tossing 3 heads with 3 coins. So first of all, what are the chances that happens? What are the chances that I get 3 heads when I flip a coin 3 times? Well, remember, that's only the chances of getting 1 heads is 50%. So to do that 3 times, then that becomes 1 out of 8 chances of getting 3 heads in a row. Okay, so that means I have 1 out of 8 chances of winning. So I've got 1 out of 8 chances of winning, which means I have 7 out of, this is a win, this is a loss. If I win, I gain what? $2. If I lose $1, right? So when I add these together, the chances of me losing is 7/8 times $1. Okay. The chances of me winning is only 1/8 times $2. So I have to take 1/8 and times that by $2, which gives me 0.25. And my chance of losing that 7/8 I would times by negative $1, which gives me negative 0.875. So when I add these together, my expected value becomes negative 0.625. Because my expected value of the 2 events added together becomes negative 0.625. And does it let me... So would you expect to win or lose money in the game? Well, my expected value is negative 0.6. How does it want me to round? Round to the nearest hundredth. So negative 0.63 is my expected value, which is losing 63 cents. Okay, so it would be negative. I guess this should be a negative. I expect to lose 63 cents. What would you expect? Would you expect to win or lose money in one game? Well, in one game, I expect to lose 63 cents. Right? In one game, I expect to lose 63 cents. But I guess that's in the overall, that 63 cents isn't based on doing this over and over and over again, right? But based on just one game, I couldn't say what I would expect because it's just the outcome. It's just the outcome of one game. Okay. So I would say where is it? Would you expect to win or lose in one game? I would expect neither. There it is. Geez. I would expect neither because the outcome of one game can't be predicted, right? You can't say that you expect to win because the probability of winning a game is greater than the probability of losing. Actually, no, the probability of losing is higher than winning. But expected value is not based on one game. Okay. So would you expect to lose or win money in 100 games? In 100 games, I would expect to lose because the expected value is negative. Okay. I don't expect to win because the expected value is not positive. Nope. I would expect to lose because the probability of losing a game is greater than the probability of winning. It's not about the probability of winning or losing. Okay. And that's where we have to be careful. Would you expect to win or lose money in one game? Well, we would expect the probability would be to lose, but that doesn't tell me about my probability of losing or winning money that doesn't give me my expected value because that's spread out over lots of games, not just one game. Okay. All right. Moving on. You are given 2-to-1 odds against tossing 3 tails with 3 coins, which means you win $2 if you succeed and you lose. This is exactly the same problem. We're not going to do another one because your answers are going to come out to be exactly the same as what we just did. So we're not going to do 2 problems. 33. An insurance policy sells for $1,200. Based on past data, an average of 1 in 50 policyholders will file a $20,000 claim. 1 in 200 will file a $30,000, 1 in 4, blah, blah, blah. What is the expected value? Well, I know 100%. I know that I'm going to spend $1,200. Okay. So I've got to add that to 1 out of 50 policyholders is going to get $20,000. 1 out of 200 policyholders is going to get $30,000. 1 out of 400 policyholders is going to get $70,000. Find the expected value per policy sold. So I'm going to take my insurance policy as this negative, and all of these are my positives because those are money gained, right? Well, I guess if I'm looking at it from the insurance policy, they're going to gain $1,200. They're going to lose all this other amount. So if I'm looking at this from the insurance company's point of view, they're going to gain $1,200 per policy. They're going to lose these amounts per policy. So my expected value, I've got to take all of those and add them together, which is going to give me a value of $475. I'm not going to make you sit through that whole thing. So I would take that $1,200 that I'm guaranteed, right? That $1,200 is guaranteed. And then I would add the 1 out of 50 times negative 20,000. And then I would add the 1 out of 200 times the negative 30,000. And I would keep going until I got all of those put in. I guess I'm almost there, so we might as well add the 1 out of 400 that's going to get negative 70,000. 1 extra 0, right? There we go. So that gives you an expected value of 475. So then it says, if the company sells 30,000 policies, what is the expected profit? Well, if they expect $475, if that's the expected value for each policy, if I times that by 30,000, I got another 0 again. Then they can expect a profit of 14250,123, right? So $14,250,000 profit. Okay, same thing for 34. We're not going to go through all of that because you just saw that example. Answer the following questions. All right, finally the fun stuff. See, this is the stuff we like. You just have to do 34 problems of crap to get to the problems that we like. Answer the following questions using a repetition, permutation, or combination. Be sure to explain why and to answer. Oh man, do we not even get to answer? Oh, we do get to answer it. Okay, good. So how many different 6-character passwords can be formed with the lowercase letters A to F if repetition is not allowed? So if repetition is not allowed and the order does matter, then that's going to be one of our NPR. That's going to be a permutation, right? Because order matters and repetition is not allowed. So in this case, we are choosing, we're choosing 6 different characters out of how many? So I'm going to choose 6 out of, we can only use lowercase letters A to F. So A, B, C, D, E, F. Oh, so I'm just choosing out of 6. So I've got 6 lowercase letters. I'm choosing 6. So I would go to math and I would go to, where is my NPR? And I'm choosing 6. From 6, I'm choosing 6. So I would have 720 different choices for a password. And I would use a permutation, okay? 36, answer the following. The president must assign ambassadors to 4 different foreign embassies. From a pool of 10 candidates, how many different diplomatic teams can she form? Okay, so order matters, right? Because she's going to send 4 different they're going to get sent to 4 different embassies. So order matters because embassy 1, embassy 2, embassy 3, embassy 4 are different. So order matters. And I'm going to choose from 10 candidates. I'm going to choose 4 teams. So I'm going to do 10 permutation, 10 P4. So I'm going to go math. I'm going to go over to probability. And I'm out of 10 people, I'm choosing 4. And the order does matter. So there are 5,040 different teams that she could choose. Assuming the president is she, right? I just noticed that. Okay. That's why I'm like, wait, why am I reading it this way? So we got our numbers. Okay, 37. Answer the following question using arrangements with repetition, permutations, or combinations. How many anagrams or rearrangements of the letters Bruce can you make? We're choosing from BRUCNE, and the order does matter because we're rearranging these same letters. So we can't repeat. So there's no repeat, and order does matter. So we're going to use a permutation again. So I'm going to do math. I'm going to go to permutations. And out of 1, 2, 3, 4, 5 letters, I want to know how many different ways I can spell those 5 letters. So there's 120 different ways that those can be ordered, those 5 letters. All right, 38. A DJ is preparing a playlist of 21 songs. How many different ways can the DJ arrange the first 5 songs. So order matters, and there's no repetition. So again, I'm going to use NPR. I'm choosing from 21 songs, and I am choosing how many different ways can the first 5 songs be played. So that's 2, 4, 4, 1, 8, 8, 0. Wow, that's 2.5 million different ways that you can choose 5 songs if you're choosing from 21. All right, let's hope that order does not matter. Good. A certain lottery has 33 numbers. In how many different ways can 4 of the numbers be selected? Assume that order does not matter. So order does not matter, and repetition does matter. So this is going to be an NCR problem because you can't pick the same number twice. So out of 33 numbers, we are choosing 4. So that's going to be 40,920 different ways that those can be selected.